Okay.
Hello, everyone. Welcome to our last spring talk at the Center of Voice Studies. I am very happy that we have Sara Marguerite Pearsell today with us. Sara is currently working at SDU, the University of Southern Denmark. She's working with Oliver Niebuhr, who we also have here zooming in, and Søren Nielsen, who's also zooming in. And Sarah is going to tell us about building a robust command inventory for human-machine interaction in noisy acoustic environments. The noisy part is very exciting because a lot of us, I think, struggle with noise all the time in different ways. And before Sarah came to Denmark, she worked at the University of Hamilton, Canada, where she also did her PhD in cognitive science of language. And Sarah has done work on perceptions of personality and dominance as well, more specifically. And crucially, Sarah has also worked on voice quality. And she also seems to be interested in amplitude in particular as well. So I'm very excited. The floor is yours.
Awesome. Thank you. So hello. Yeah, I'm working with Oliver Nieba on building this robust command inventory that right now we're focusing on industry, but it's also going to be useful in other fields as well, which I comment on at the end. So there, okay, perfect. I was like, oh no, it's not moving. Yeah, so my background, just to go a little bit further into sort of my research that I've done. In my undergrad and a little bit after my undergrad, I partook in an independent project where I looked actually at speech automaticity, and we ended up using dual task paradigms. This is a lovely photo of me hooked up with all the coil sensors for the electromagnetic articulograph, which maps out in very, very accurate measurement XYZ space. So you get a nice three-dimensional aspect. And it's great because it actually picks up, as you can see on the picture on my tongue. So you can get nice understanding of what your tongue is actually doing when you're making productions. And basically, in that, we got 16 different channels of information from all these different electrodes that are at different parts of your articulators. And we're basically found at the end of that, I mean, it makes sense that if you have automaticity, you have less cognitive load that's being put on your system when you're actually doing production of any sort of physiological speech going on. For my master's, I looked at flapping in Canadian English specifically. And during that time, I used Pratt as well as high quality audio recordings to actually go through and measure and analyze the sort of different speech patterns that I saw of Canadian speakers. And then for my master's, for my PhD, at McMaster, I actually looked at sort of the physiological aspects of speech and how they affected personality trait perception. Specifically, charisma was a large focus of what I was looking at, but I also looked at other aspects like dominance, using the big five of personality to sort of more easily ascribe what that means. And I did all sorts of things with that, including measurements on Pratt and voice sauce to look at different spectral aspects, as well as acoustic information that were in the speech signals. And there's a couple of different measurements listed there. And the sort of three physiological features that I looked at were voice quality, as well as loudness variations and allophonic variation as well. So the current research that I'm doing is with the Arrowhead Project. And just to sort of, for those that don't know, the Arrowhead Project is an EU-funded group that's actually doing a bunch of different projects that are hoping to have sort of automatized and digitized tools for the European engineering industry. And so, what I'm specifically focusing on with my group is building an acoustically robust inventory of commands that are actually going to be resistant to noise that occurs in these sort of industrial settings as well. And Solon, who's here, is actually part of Sound Focus, which is one of the other groups that we're partnering with in order to run some experiments, which is we're meeting up tomorrow and hopefully going to form some experiments as well. So the big question I think that people kind of always ask me when I tell them that I'm researching this is why speech-based commands. And there's a couple of different reasons why speech-based commands are important. So first one is it allows workers to have mobility so they can actually move around on the floor, on the workspace floor. Um, and sort of as a consequence to that, it also reduces this restrictive sort of current paradigms that exist where individuals are getting stationed at machines to hit a button manually. So it helps eliminate that as well. It also allows for faster response times for interference or for implementation of commands. So instead of having to run over to a machine to turn it off, you could actually just use one of these command words to stop the machine. And taking sort of all of it in together, when you look at these different aspects, it actually can do things like increase efficiency on work floors. It can also for employers have the benefit of creating faster response times and things to make more revenue for them. And for workers, it's also beneficiary because basically they don't have to get stuck in a spot. So it reduces cognitive load. It helps them have the ability to move around, be less stationary, and have physical aspects affected as well, like if you're sitting or standing all the time. And so, in order to develop this command inventory, one of the first things that we focused on was using linguistics in order to determine exactly how we were going to construct this, what kind of words we were going to use, etc. And so these are sort of some of the features that we considered, as well as many others, but these are the sort of large overarching ones that we started looking at. So the first thing that we decided was we wanted to use non-words. And part of the reason we wanted to opt for non-words is because we want to have an inventory that's accessible by many different sort of language speaker backgrounds, as well as many different types of factories or industry, for example. We basically want the words to lack meaning or previous association so that it's easier for this multilingual sort of reachability. And non-words basically mean that they're not real words, but they could be real words. So we took a lot of other features that we considered both across language backgrounds, such as what the phonemic inventory is, so what phonemes are actually found, what sounds are actually found in these languages that we were interested in, as well as syllable structure, for example, things like having consonant, vowel, consonant, which is what we found to be the most sort of across the board, universally acceptable structure, were things that we took into consideration for building it. And also having it be easily pronounceable. So making sure, again, back into that phonemic inventory to make sure that we're not picking a retroflex R like in English and then expecting individuals that don't have even an R maybe exist at all in their phonemic inventory to be able to pronounce those words, for example. We also wanted to make sure that they're acoustically distinct from one another. And I put this picture, these two pictures on the right up just to sort of, not that I think I need to go super in detail with the linguists, but just as a general sort of understanding, the lower image of the oral cavity there shows vowels sitting at sort of very far away points, so as distinctively, acoustically distinct from one another. So E, which is in the front and high, U, which is in the back and high, and Ah, which is low and front or mid, depending on who you're talking to. And I also have this illustration of the waveforms up on the top there on the right to basically show if you have a word like pin versus fun, if you're looking at the vowels there, the I and the and you can see the different bands of harmonics there and how they actually show where in the mouth they're sitting. You can see you have that distinctiveness in terms of where it's located in the oral cavity. So using things like that to our advantage when you're competing with an acoustically noisy signal, we at least hypothesize that it could be beneficial when developing an inventory, just because right now there isn't a lot of research, especially with specifically industry noise. Also, as another kind of example, looking at the plosive p and the fricative fa, you can actually see where it's sitting in the spectral signal in terms of energy, as well as the length of it as well, considering aspects like that as well. So basically, our starting point is taking linguistic knowledge as well as signal processing background and putting them together in order to develop and then basically test and inventory an industry noise, which is what I'm working up to right now with talking about our first couple of experiments that we've run. So the completed experiments that we've run to test our sort of proposed inventory list is we've run two different ASR systems and speech recognition of words within industry noise, specifically factory noise. And we've also done a linguistic symbolism test. So the first experiment we did used two ASR systems. So we used Google Translate and Apple Dictation. And the reason that we chose these two is they're easily accessible, they're widely used, they're at your fingertips. And as a preliminary starting point, I think it's a good place to look at because they're so easily accessible. If you're dealing, especially in places like industry, that might be what they opt for rather than a more complex sort of ASR system that's programmed, et cetera. So we thought as a jumping off point, this was a good place to look into. And just for those that aren't familiar sort of with how ASR systems work, I just put a nice sort of simple model of what it kind of looks like to function in ASR and how the speech signal gets sort of processed. We also did it in three different types of noise. So we looked at white noise, we looked at speech shape noise, and we looked at industry noise, which is our main focus. But we also thought it was important to look at other different kinds of noise to see if we're getting similar results, how they compare and contrast. We chose three different acoustically distinct industry noise out of a large selection that we've professionally recorded at SDU. And these are a short sample below there of each of the ones that we used for this particular one. And it's just interesting to note that they do take up a large portion of the spectral energy, but they also have different spectral energies. And that's what we were kind of aiming for, was to get a variation of industry noise. So we can see how it performs, if it performs in the same way, and how it varies, etc. I will also quickly add before I get into the next slide, because ASR systems work with real words and we're using, as I mentioned, a non-word list, before we started the experiment, we actually created a set of real words that matched as closely as possible to both phonemes and consonant structure, syllable structure. So on the next slide, you'll be able to see it. I'll show you the words that we chose, and they matched pretty similarly, just as a general gist, because otherwise our ASR systems wouldn't be able to recognize anything and the results wouldn't mean anything because ASR systems recognize speech and words. So here's a map of the results. I'll explain kind of how it's broken down here. So if you look on the left-hand side, all of our real words are on there. So like walnut, soccer, sidewalk, shoes, seesaw, sea salts, refund, raindrop, etc. We have it split by the two ASR systems. So for the first two rows, we actually have the Apple um, dictation, and then the bottom two rows we have the Google Translate. We also have it separated by noise type. So you have white noise here, speech shape noise, and the three different types of industrial noise as our columns. We also have them separated by gender. So our blue represents male and the red represents female. We did male and female as well to see if aspects like fundamental frequency affect any way the recognition just because they're functioning at different hertz as well. We were interested to break that down too. We have it separated down here by our baseline at 0 decibels. So we did a test of just no noise to make sure that the ASR system could actually recognize the word. And then we did it up by 3 decibel intervals, starting at 64 decibels. The voice, when it was produced, was at 70 decibels. So we wanted to start a little bit below the thresholds of where the voice was actually being produced at and work up from there to sort of see where the line starts to have issues of recognizing what's actually being produced in the noise. And We also, just to note, because there's numbers on here to explain the colors, basically each of the words was run 3 times with the ASR system, and it was given a score of 3. So if the 3 is there, it means it was a perfect score. The ASR system definitely recognized the word that was being produced. If it was a 2, it recognized it 2 out of 3 times. If it was a 1, it recognized it 1 out of 3 times. And if it was a 0, it failed. You can also notice that there is chunks of white. That means that the system started to deteriorate rapidly, and we just didn't run it because it was 0 across the board, just to sort of clarify. Is everybody good for me to move on? I don't want to go too fast. It's a lot of information in one chart. But yes, so we looked at the results and we sort of found general things out. So the first thing that we found is that female voices are more accurately recognized in most word conditions, and the gender is up on the top here. We also found that Apple ASRs generally did better overall, and it's down here. You can see it here. But Google ASR excels in speech babble noise, and with male voices. And I mean, when you kind of look at what the purpose of the ASR system, it does make sense that Google Translate, which is focused on translation, they even have a feature where you can do back and forth conversations. It does make sense that this one would function better in the speech shape noise than perhaps Apple. We also found that noise level strongly affected recognition, with industrial noises being the most challenging, which is not super unsurprising, I should say. And we also looked at other things as well, such as linguistic features like word sonority, duration, and frequency. And we found that they improved recognition as well. And Google ASR had more benefits from sonority and duration as well. We also did a linguistic symbolism experiment, and we had 100 participants from 10 different language backgrounds. So we had 10 participants per each language group. These were things like Urdu, Hungarian, German, Danish, etc. So we had 10 different ones. And basically, what we wanted to look at this was to see if there was any natural connections that occurred with the non-words that we gave to commands. So we had a list of 17 commands that are common commands that we found when we were doing our recordings on these industry floors and these factory floors. And some examples are like up, left, increase speed, stop, emergency, rotate, things like that. So we narrowed it to about 17 that we saw over and over and over and over again. And we had an audio recording of all of our non-words and actually did an experimental design where they didn't see any participants didn't see any of the words. They only heard them so they could play. And we asked them to match up one per one, so having like one-to-one relationships, so 17 non-words and 17 commands, to see if there was any sort of relationship. And we just asked them whichever sounds basically like what you think sounds the most like or you would associate most with a command. And we took the results from that and ran an analysis as well. So we did a quick visual initial analysis. So if you look at the bottom, down the bottom here is all of our different commands. So we have like cancel, decrease, speed, display, and then we have our non-words listed on the in the chart there as well. So all the colored bars. And so just to note, there's a much larger list, but some non-words actually just were never picked for any of the commands, which is interesting. So we also found that certain non-words had stronger associations with specific commands. So if you look at right at the bottom, which is like here, um, you find that a word like refad, the non-word refad, is strongly associated with it and rotate as well. So we did find strong associations for certain non-words and certain commands together, at least on visual inspection. I'll get to the analysis in a second. We found that some commands like hold and increase speed had responses that were spread across multiple non-words, which meant that we didn't see a single non-word as being strongly perceived as a natural match. And then we kind of summarizing, we found that there was higher some commands had higher responses for specific non-words, while others had lower, others were lower and had lower responses, meaning that they were more varied or uncertain. And also, we found that some non-words were never selected too. And so, looking into the statistics a little bit more, we did a chi-squared test that found that certain non-words and certain meanings were significantly non-random. We also did a breakdown. I didn't put it in detail here, where we actually broke down the different kinds of commands into sort of semantic categories and semantic fields. We had like motion, activity, adjustment, direction, and interface or safety. And we found that there was always at least one command or one non-word that was strongly associated within that type of command, which is positive. And we also looked at things like open vowels and obstruents and found that non-words that had open vowels and obstruents were more often linked to adjustment, interface, and safety. And non-words with sonorants and closed vowels were often linked with motion, activity, and direction. So it's interesting because it kind of shows that there is some sort of categorization that's happening, and there is some sort of relationship, whether it's to the word or the category, maybe more generally, basically. So this is, I think, a positive kind of information that we can take to now integrate in the next steps, our two experiments. So we do have some future experimentation that we want to do. And this, we are running this actually on Wednesday coming up. We have a automated version. The last experiment with the ASR system, I ran it manually, which was very time consuming and tiring. And so we actually have someone that programmed to run automatically for us, and we're going to test several ASR systems. So it'll be much quicker, much more efficient. We also are going to be running a automated phoneme recognizer instead of an ASR, which is going to be great because we're hoping then that we can actually have recognition of the specific phonemes and be able to run a non-word chunk as well to see how it performs in noise. And we also did recordings with these non-words from several different language backgrounds, speakers. So we want to do some analysis on that to sort of see what sort of spectral matching that we have in order to make the non-word command list more robust for users as well. And sort of the accumulation of it all is we need to test this in the sort of real environment. So this is all working up to justification and explanation and this sort of experimentation result power to actually justify bringing this onto factory floors to implement and run this as well. And just to kind of add in, this isn't just industry, it's also brings sort of opportunity to provide other feedback to other fields as well. So like assistive technology optimization, so understanding sort of how noise robust ASRs can improve things like voice controlled assistance devices and like or hearing devices in real world environments, which are really noisy and often have a lot of industrial noise as well too, like hospitals or classrooms maybe that are extra loud or near certain mechanisms that are loud. It also can help with sort of sound symbolic non-words to help create learnable cross-linguistic commands that could be used in things like therapies as well as with different devices. Um, we separating by gender as well, I think also provides opportunity to have more investigation into ASR designs that are separated by different features like gender or other vocal features to give us more opportunity to have more adaptive and equitable ASR systems for a diverse set of patients, for example, and as well as noise and speech training, so like industrial noise testing, so we can have more effective therapy programs as well, and having the opportunity to have non-words that are useful and intuitive to build sort of tools that can be used for auditory or cognitive processing that's also interlinked with technology potentially as well. And that is all. Thank you.